Live from the BBC, The Naked Scientists.
Hello and welcome to this week's edition of The Naked Scientists with me, Dr. Chris Smith, and with Phil Rosenberg.
Hello, Chris.
On this evening's show, space science. We're going in search of our origins. We're looking at the science of meteorites, the science of satellites, and also finding out how we can avoid Armageddon. What happens if a massive great thing is going to slam into the Earth? Can we avoid disaster? That's all coming up tonight. If you have any questions for us, our guests on tonight's show include space scientist Maggie Adairian. Good evening, Maggie.
Good evening.
Maggie's a lovely lady, and she would love to hear from you about anything to do with how you make satellites, because you're designing one.
Yes.
You're going to talk about how you actually put them in orbit and all that kind of stuff and how they work.
We make very small subsystems for European Space Agency satellites, but I can tell you about what we're doing.
Brilliant. Our other guest this evening is Ian Sanders, who's come all the way from Trinity College Dublin in Ireland. Good evening, Ian.
Hello, it's nice to be here.
And he works actually specifically on meteorites. So if you want to know what's meteors, so if you want to know what's coming slamming into the Earth and zipping across the night sky and what they can tell us about space science in general, he's your man. 08459 is the phone number, 08459 25 2000, or you can send in an email, chris@nakedscientist.com.
And also tonight, we've got the ThinkJet printer. That's a printer that doesn't use any ink at all, but actually can print out brain cells. We've also got a concept for a new mission to Mars that will literally crash into Mars looking for water ice. So, also tonight, if you can give us a call, any questions that you've got on space science, medicine or technology, just give us a call at BBC Local Radio in the East, and that's at 08459 25 2000, or give us an email at chris@nakedscientist.com.
And later this evening, on Kitchen Science, we'll be joining the guys at Billericay School in Essex to find out how to make your own fibre optics. Derek and Dave are there right now, and they'll take you through it. All you're going to need this evening, if you want to get prepared early, is a lemonade bottle, anything that you can put fluid into, basically, and make a hole in the bottle. So preferably not a wine bottle that's made of glass, if you can help it. So preferably a plastic bottle that you can put water in, and a torch. That's coming up shortly. And our quiz this evening, Science Fact or Science Fiction, we give you some easy scientific facts, and you tell us if they're true or if they're false. And if you get tonight's top score, we've got some great prizes for you. We'll be sending you down to London. You can go to the IMAX to see a 3D movie, or we also have some vouchers from the Wiggly Wigglers to have your garden growing better than the Amazon rainforest.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Now, you've all heard of an inkjet printer, but now meet a ThinkJet printer, because scientists in London at the University of London, a group of them including Peter Eagles, Amer Qureshi and Suhan Jayasinghe, have come up with a way of modifying an inkjet printer and turning it into something that can print brain cells or even white blood cells. Now, what they've done is to work out how to use electric fields to produce tiny droplets from a suspension. So what you can do is to create a collection or a suspension of cells at large numbers. You feed them into this very clever nozzle in this device, and it sprays those cells out onto a surface, and it uses a high voltage potential difference to do that, and it therefore prints the cells onto the surface, and they remain viable and they remain alive throughout. And why this is important is that scientists think they could be able to use this technology in order to rebuild tissues, literally cell by cell, in 3 dimensions. So that means if you lose a part of your brain, it might be possible to reconstruct it anatomically correctly using techniques like this. Obviously, it's at very early stages so far, but still very promising nonetheless. To put it simply, how it works is that you charge the solution of cells to a very high potential, about 30,000 volts, and you make the thing you want to print the cells onto at the negative, a 0 voltage. And so there's an electrical attraction between the two surfaces, and it pulls tiny droplets containing the cells onto the surface and then puts them down. And they've done tests so far with brain cells from mice and white blood cells from humans, and the cells seem to survive the technique, and they seem to be able to grow and proliferate afterwards. So that seems like good news. I wouldn't actually suggest that you have a brain hemorrhage right now if you can help it, because it's going to be a little while before they've honed down this technique and got it into the clinic, but certainly very promising. Phil?
OK, we've also got a new spacecraft that's been designed for launch to Mars, potentially. It's in the running, created by a guy called Phil Christensen at Arizona State University over in the United States. And this spacecraft, if it's selected, will use an ingenious new way to actually look below the surface of Mars. Now, what it's going to do is search for underground ice by smashing a 100-kilo copper ball into the surface at about 15,000 kilometres an hour. That's going to create a crater about 50 metres across and about 25 metres down. Now, while that's all going on, there's going to be another spacecraft in orbit looking down at the surface, looking at what's thrown out and looking at what's in the bottom of this crater, using spectrographic techniques to look at the colours and the light that's coming off the material to see if we can find water ice under the surface on Mars.
Why are they interested in using copper? Why not use any old substance? Copper's quite expensive.
Copper's also actually incredibly dense, which means it's really good for taking. We can make it into a small, compact ball, and we can launch it with a high momentum and a high energy, which means that we can get a really big crater for quite a small ball.
And what sorts of chemical fingerprints are they going to be looking for in order to determine that there was or wasn't potentially life on Mars?
Well, this particular mission, it will be able to look for things like carbonates and features that are on Mars that possibly have carbon in them that could be evidence of either past life on Mars or possibly just the existence of liquid water on Mars and the way that they're formed. But mostly this mission is going to be looking for water ice. Now, if there's water ice on Mars now, there's a good chance there was liquid water on Mars in the past. And if there was liquid water on Mars, then there's actually a fair chance that maybe there was life.
Yeah, because Mars is probably viewed as the best candidate in our solar system for the elaboration of life, not just second to Earth, isn't it?
Yeah, absolutely. I mean, there's been a lot of interest in the past sort of 2 decades about looking at whether life could have existed on Mars. There was a meteorite that was actually once found on the Earth that actually had what looked like a fossil in. Now, we actually managed to prove that this meteorite came from Mars by looking at the gases that were trapped in the meteorite and comparing them to samples of Mars' atmosphere that we've measured remotely using a spacecraft. Now, once we can do that comparison, we know it's come from Mars, and we found what looks like a fossil of a bacteria, called a microfossil. A lot of controversy about whether that's actually really a microfossil or whether it's just a figment of the imagination or an optical trick. But it could be that there was life on Mars at one particular point.
Maggie?
Yeah. The idea of finding water on Mars, to me, is so exciting, because it sort of brings up the whole idea of terraforming. If we are going to sort of journey to the stars, sort of the next stage of our perhaps evolution, finding water on Mars makes life so much viable on Mars, which I think is why scientists are so excited by this sort of thing.
Because it's the one thing we absolutely need, critically,
Yes.
isn't it, to human existence?
Quite. You can survive a long time without food, but only a few days without water. And water is the basis for all life, as we know it anyway.
It's The Naked Scientist, Dr. Chris, Dr. Phil. We're here with you until 7 this evening on BBC Local Radio right around the eastern counties. If you have any questions for us about science, technology and medicine, not just space science, call them in and we'll slot them in during the programme. Our phone number's 08459 25 2000, or you can email me, chris@nakedscientist.com. Now, it's been another exciting week this week for people who love snails. And if you wind the clock back to the time of Charles Darwin, and he was the forefather, really, of the theory of evolution. He wrote that famous book, The Origin of Species. Charles Darwin was fascinated by the question of, if you go to a remote volcanic island somewhere in the middle of nowhere, you can inevitably find snails living there. Now, how did those snails actually get there? That island has never been connected to the land in any way. It's sprung up from the seafloor as a volcano. And the snails that Darwin saw there, in the middle of nowhere, look terribly like snails found elsewhere on Earth, but many thousands of miles away. Well, Darwin suspected that they probably were the same species of snails, and perhaps somehow they've managed to stow away from Europe to wherever they ended up. But how did they do it? Snails can't swim, and if you put their eggs in salt water, they die really quickly. Well, Darwin thought perhaps they took a lift on a bird. Perhaps they stowed away aboard a bird, of the most primitive form of flight that there was, really, before BA came along. Well, that mystery is laid unsolved for some 150 years, but now scientists here in Cambridge, led by a guy called Richard Preece, collected samples of these snails down in the Tristan da Cunha Islands, which are halfway between Africa and South America in the Atlantic, and they genetically fingerprinted them. And they showed that they're genetically very similar to the snails that we find in Europe. And what this shows is that they really did make that journey, which makes Darwin's suggestion that perhaps they went by bird even more likely. Richard Preece talks to us about it now.
We wanted to understand how the snails on the Tristan da Cunha Islands, how they got there. We had suspicions that they might be related to a species that occurs in Europe. But what we've shown here is that those suspicions are very well founded. They are indeed exactly the same genus as the European one.
So, the outstanding question, how does a simple snail, which doesn't have wings, it can't swim, how do you think it got there?
Well, the most plausible way of getting there is to hitchhike a ride on some migratory bird, maybe a wader. Wading birds are often found as stray vagrants on mid-Atlantic islands, and that would seem to be a most likely vector.
How big are these snails, then?
The adult snails are 7 millimetres, maybe a little bit more when adult. These snails presumably weren't transported necessarily as adults. They might well have been transported as eggs or as juveniles. And one of the things about these particular group of snails is the fact that they have a very sticky slime. It's very noticeable if you tap them. The slime is tenacious and will stick to your fingers very, very readily.
So you think that one of these young snails would have potentially stuck itself onto a bird at some point somewhere in Europe and then made its way ultimately 9,000 kilometres to the Tristan da Cunha Islands?
Well, it may not have done this in one leap. We know that these snails are hermaphrodite, and so that you only need a single individual to found a colony. That's quite important. And it's quite interesting that this genus of snail also occurs in North Atlantic islands, particularly on Madeira and on the Azores,
so
where there are two
they
species.
might have been some kind of stepping stone down there then?
They could have been a stepping stone, yes.
Just to play devil's advocate for a minute, how do you know that this wasn't, say, a boat?
We know that the Tristan da Cunha Islands, for example, were only discovered in 1506. So the evolutionary changes that we've found in these species, for example, on the Tristan da Cunha Islands, there are 8 of these species of snail, and clearly it is unprecedented for 8 species of snail to have arisen in the 500 years that has elapsed since the discovery of the islands.
So when would that put the time at which these snails first took up residence?
We haven't got an accurate molecular clock to be able to pinpoint that, but perhaps in the future we might be able to get a better handle on that.
And given that these snails have travelled so far, does this make them the world's longest hitchhikers then?
Well, I think for a snail, I don't know of a better example. It was quite interesting that way back in 1921 there was an article in Nature reporting for the first time the occurrence of one of these snails on the top of the mountain on Madeira. And the article was claiming that that was an example of transportation by birds to that remote mountain peak. What we've shown here is not only were they able to get to Madeira, but they were able to get a good deal further, right across the equator and right down into the South Atlantic.
So Naked Scientists, Dr. Chris and Dr. Phil, talking there with Cambridge University's Richard Preece about how snails could have possibly stowed away aboard birds, just as Darwin speculated 150 years ago, and found their way onto the remote Tristan da Cunha Islands.
The Naked Scientists, supported by the Wellcome Trust.
We are here with you through until 7 o'clock this evening. We're taking your science questions on anything science, technology and medicine, but we have a special slant tonight on space science because we have with us Maggie Adair and Ian Sanders, and they're going to be talking about really the origins of where we all came from, how we can find things in space that tell us about that, and also satellite science. How do we make satellites, how do they work, and how do we put them into space, and where are we going with them next? If you have any questions on those kind of things, 08459 25 2000, or send me an email, chris@nakedscientist.com. Talking of emails, I have to say hello to a couple of people who've been kind enough to write to us from Hawaii. Michelle Harmon is in Hawaii, and he says, Oahu, that's Hawaii. Hello. And I've just started listening to your show and I love it. Informative, funny, and it's very entertaining. Much mahalos, which is thanks and appreciation for all the hard work you do. It's cool to get people of all ages involved in learning science, and the podcast being there for people all over the world to listen to is great. What an inspiring programme. So thank you very much for that. The check's in the post. Another one from Bill Martin, who's also in Hawaii. He says he's in Curtistown, near Hilo in Hawaii, and he was enjoying our stuff as well. So thank you very much for both of you. If you'd like to drop us a line and tell us what you're up to around the world, wherever you're listening to us, please write to chris@nakedscientist.com. And if you're a scientist, why not record something about your work, a 1.5-minute podcast, if you will, send it to me, and we'll broadcast it here on The Naked Scientist.
We've got a question here from a regular listener too. It says, "Hi Chris, I listen to your show every Sunday. I was just wondering what grenades are made out of, and why does it take a while before it blows up after the pin is taken out?" That's from Liam in Skegness.
Any ideas?
Well, I would guess there's some sort of timer in there, but I'm not quite sure how it would work and what exactly it would be made of.
Yeah, well, if you look at a hand grenade, actually it's a bit of like an egg, isn't it? So it's got a hard metal shell around the outside and it's packed with high explosives. But at the top there's a trigger, and on that trigger there's a really big spring, and the spring pushes down on a hammer, which runs down inside the hand grenade. Now, when you hold the handle closed and the pin is in it, the spring is compressed and can't go anywhere. But as soon as you pull the pin out and let the handle up, it drives that hammer down inside the core of the hand grenade. And in the bottom of the core of the hand grenade is a little detonator. And it fires that off, and that lights a fuse. And the fuse burns slowly for X number of seconds, however long the hand grenade has been designed to burn for, before it goes off. And that fuse then detonates the main detonator and charge, which is round the corner, if you like, a certain time later. And the idea is that you obviously know roughly how long it takes to go off, because then when you lob it, it doesn't have any opportunity for the enemy to pick it up and throw it back to you.
Sounds quite clever.
Yeah,
It's definitely worth avoiding holding on for it too long.
Right, I told you we're going to be teaching you how to make your own fibre optics this evening, and at Billericay School this evening, Derek and Dave are with pupils down there to teach you exactly how to do this. This is kitchen science, and if you'd like to have a go at doing a bit of amateur experimentation on your tabletop tonight, you could win yourself a fantastic prize if you're first through on the telephones with the correct results to our experiment. So all you have to do is do what Derek and Dave tell you. You're going to need a bottle, like a lemonade bottle or a Coke bottle or something you can see through, and a way of making a hole in it. But Derek, are you there with us this evening in Billericay?
Hello there, yes, and welcome to Billericay School. And there is some very, very good feeling here. We've got some students here who've been good enough to volunteer for us on this Sunday evening. Hardcore, I say, so that's brilliant. We'll be meeting them in a moment. Firstly, of course, Dave is here with me as well to tell us what we're going to be doing today. What's up then?
Well, this evening, Derek, we're going to be building our own fibre optics out of just a lemonade bottle and some water.
Fantastic. OK, and we've also got 3 helpers, all from Year 12 here at the Billericay School. So could I just get you to give me your names, please?
Rachel.
Andrew. Simon.
Excellent, guys. And can you just quickly tell me, Rachel, firstly, do you do science?
Yep, I do biology.
OK, and yourself, Andrew?
Biology and chemistry.
OK, and is Simon going to trump that?
No, just do biology.
OK then, yeah. But do we all like science here?
Yep.
Yep.
Absolutely.
Oh, that is very heartfelt there. That's brilliant. OK, so then, what we're going to be doing today, you can do this at home too. So please, why don't you get these things together and you'll be able to build your own fibre optic at home. What you need is a lemonade bottle or some kind of plastic bottle which is perfectly transparent. OK, the larger the better as well. Something to make a nice round hole in it with. Dave's got his drill standing by, but anything will do. But please, adults standing by to supervise with that if necessary, that would be great. And a torch of some sort. And it's best to do this in the sink. OK, otherwise, if you can get all those things together, listen to what Dave tells us to do.
First thing you need to do is to take your hole-making device and make a hole maybe 5 or 6 millimetres across down near the bottom of the bottle. So I'll do that now.
OK, so here's Dave with his drill, and here he goes. So Dave's basically whacked his drill straight through the bottom of that bottle. So it's not actually on the base of the bottle, it's on the side of the bottle, but very, very close to the base. So the hole is kind of pointing out to the side, and the hole is about 0.5 centimetre across. All right then, and what next?
OK, now, Rachel, if you'd like to fill the bottle up with water.
OK, and of course some water will probably come out the hole, so do they need to cover the hole?
It would probably help. Right the way up, fill it right the way up.
OK, so maybe cover the hole with your finger and fill it right the way up with water otherwise.
Is that enough?
Yeah.
That is brilliant. OK, so that bottle is absolutely full and the hole is covered, so no water is coming out at the moment. OK, and then we're not, of course, going to do this experiment now because we want people to do this at home, but what should people be doing?
What you want to do is get the torch, shine it at the back of the hole and let the water come out and see what happens.
OK then, so what you've got to do really then is have a torch pointing through the bottle so that the light actually shines out of the hole that you have made. So that actually the light really goes kind of into the bottle from one side and then out of the other side, shining out horizontally. And then as you actually let go and let the water flow out, you've got to tell us what happens. And of course you must phone in and tell us what's going to happen as well. So the number is 08459 25 2000, and you can also email us if you like. It's chris@thenakedscientist.com. The guys here are ready to do that, but we don't want them to do it now, of course. We're going to do it later on in the show when we come back to Billericay School to find out what happens and an explanation from Dave. Other than that, nothing more to be said, except maybe another cheer from Billericay. It must be the most enthusiastic place we've ever come to. So otherwise then, back to you in the studio.
Thank you, Derek. Derek and Dave at Billericay School in Essex, finding out how to make their own fibre optics. Have a go at the experiment. Just do as they say. Get a drink bottle, fill it with water, put a hole in the side and shine a light in. What happens? Phone now, 08459 25 2000, or email us, chris@nakedscientist.com. The first one through with the correct observation, and you win yourself a prize. And the prizes up for grabs tonight are tickets to a 3D movie down in London. That's at the IMAX. Absolutely fabulous. You get to wear these really funky glasses which make the whole of the screen come out to meet you, and you really get to sort of interact with the film in a new way. That's amazing. Got to be seen to be believed. Call now if you want to have a go and try and win those. You can also win them through having a go at our competition, Science Fact or Science Fiction. The phone number 08459 25 2000. Now I have to say hello to Majid Matari, who's in Mashhad in Iran. He's listening on the podcast. He says, "Hi, Chris. Thanks for a wonderful show. Recently discovered your podcast and I enjoy it enormously. So pleased to hear that we're reaching Iran as well. So thank you for writing." Now, as we mentioned earlier, we like you to send in podcasts if you're doing something interesting scientifically, and we broadcast them on our programme. And we're in the middle of a series with David Lemberg. Dr. David Lemberg is an expert on nanotechnology, and he also runs a programme called Science and Society from scienceandsociety.net in the US. And we've now got to part 3 of his series on nanotechnology, in other words, small technology and how it can be applied to various things here on Earth and in space. And this week we're going to take a look at what nanotechnology can do for the space race.
The costs of space exploration are now a key factor in what we can and cannot do. It costs $10,000 per pound to launch to near-Earth orbit. It costs $100,000 per pound to launch to Mars and Jupiter. So lighter and stronger materials are critical to advancement of NASA's and the ESA's space programs. NASA is engaged across many fronts, making nanomaterials for instrumentation, propulsion, navigation systems, and sensors. Carbon nanotubes are the ideal substrate. A carbon nanotube is essentially a sheet of carbon atoms that curls up into a tube. These tubes are super strong, super light, and super flexible, a remarkable set of physical characteristics. Carbon nanotubes are 60 to 100 times as strong as steel, and they have excellent conducting properties, so they are great for electronics. As an example, NASA is developing carbon nanotube-based small X-ray tubes for use in the 2009 Mars missions. Remember the X-ray tubes used on the Mars rovers Spirit and Opportunity? These new miniature high-performance machines will fit in the palm of the hand. Also in development are tiny gas sensors the size of a computer chip for analyzing atmospheric composition. Nanotech designed sensor networks will obtain global planetary information on topography, atmosphere, and signs of life. Well, that's a few of the paradigm-shifting advances we're looking forward to in the exploration of space. Next week, we'll look at breakthroughs in computing.
Dr. David Lemberg from scienceandsociety.net taking a look at what nanotechnology can do for the space race. Now, we are, of course, talking space science here on The Naked Scientists on BBC Local Radio right across the eastern counties. And if you want to join in, 08459 25 2000 is our phone number, or you can email me, chris@nakedscientist.com. It's Dr. Chris, that's me, and Dr. Phil. We're here with you until 7, and we'll be talking very shortly with astronaut from NASA, Stan Love, who's in Houston, Texas, and he's going to tell us how to avoid the next Armageddon. We'll also be talking to space scientist Maggie Adarin about satellites and how you make one. Make one in your kitchen with Kitchen Science next week, perhaps. And also we'll be talking to Ian Sanders, who's from Trinity College, Dublin.
Sorting out the sparks from the quarks. The Naked Scientists.
Dr. Chris and Dr. Phil, we're here with you until 7 as The Naked Scientists right across the east of England on BBC Local Radio. Joined this evening by special guests Maggie Adarin, who's a space scientist, and Ian Sanders from Trinity College in Dublin, who's an expert on meteors, and then they become meteorites when they land on Earth. Good evening, Ian.
Good evening.
Tell us a bit about your field. What do you actually do?
Well, I'm a geologist, and meteorites are rocks, and so those are things that geologists study.
So where do you go to find them? Because I've heard that the South Pole is a really good place.
Yeah, remarkably, probably about half the meteorites in the world's collections are from Antarctica.
Is it just because they're easy to see, because they're black on white?
Yes, but it's the story's a little bit more subtle than that. Of course, they land on the ice and they immediately get buried by more snow and they would disappear. And the ice in Antarctica is about 4 kilometres thick, and it's creeping out under its own weight and breaking off around the edge of Antarctica as icebergs, and of course the meteorites in them would just end up on the bottom of the sea. But there's 1 or 2 places where that ice rides against a mountain range, a buried mountain range under the ice, and that forces the ice up, and the wind blowing over the surface, it's a very, very strong katabatic wind in Antarctica, and it evaporates the ice. So deeply buried ice ends up coming back up to the surface.
And bringing with it a present from...
That's exactly it. And once they get to the surface, they're stuck. They can't go anywhere. And so they accumulate in these places where the ice is evaporating. And it's possible to identify them because they're blue. You can identify them from space and send in search parties specifically to those blue ice fields and go around on skidoos and collect everything you see.
So even Maggie can help you here by looking, just spotting them from space. Is it really? I mean, you can use cameras on satellites mounted in space in order to spot a meteorite, a speck of dust, really.
Well, no. From space you spot the ice field, the blue ice field. You know where to go.
The resolution would be a bit hard.
But presumably, Maggie, the spy cameras could do that, couldn't they? Because they can read the text on a newspaper, some of them.
Well, there's lots of hearsay and lots of sort of science from the movies, and it's trying to draw the line where what's reality and what isn't. What the military is capable of is hard to define, but we can get to better than 1 metre resolution with sort of standard space cameras these days, and we're working on improving that as well. So if you think of sort of a 1 metre square as seen from space, wouldn't be able to quite resolve the print on a newspaper, but you'd be able to tell quite a bit, building densities, things like that. So that's the sort of level we're working at the moment.
So in the meteorites that are being dug up and found on the surface in Antarctica, how long have they actually been in the ice then? How long have they been on Earth for by the time we find them?
That's a good question, and remarkably, scientists have a handle on that. They think they go back tens of thousands, hundreds of thousands of years, maybe even as much as 1 million years. And the reason they know that is that while they're in space, they're picking up radioactivity from cosmic ray bombardment, and the longer they're sitting in space, the more these new materials, new atoms are made, and it's possible to measure just how much is accumulated in the material, and that
sort of like a radioactive clock.
Yes, it is, and it tells how long it's been sitting on Earth since it landed.
Now, in the context of the meteorite that Phil was talking about earlier, which came from Mars and which people thought there might show signs of life, an obvious question to ask is, well, how did something from the surface of Mars end up on the surface of Earth? In other words, did something slam into Mars and release that piece of rock, which then ended up drifting around in space for a long time, and then we picked it up like a giant Hoover? What happened?
That's pretty well it, yes. But for a long time, it was a bit like bumblebees can't fly. You know the story. It couldn't be possible, and scientists said it wouldn't be possible for an impact into the surface of Mars to actually launch a piece of Mars at more than Mars's escape velocity. But indeed, as you said, these meteorites that we think come from Mars were proven to come from Mars from this trapped gas, which is identical to the gas that was measured on the surface of Mars back in 1977 by the Viking lander. So we know it comes from Mars, and therefore that's the only mechanism. The big meteorites struck the surface of Mars, caused a crater, and ejected pieces from near the surface. They went into orbit. They probably stayed in orbit around the Sun, and eventually got picked up on Earth maybe a few million years later.
Okay, so we are happy that these are the things that are landing on Earth. They make nice bright lights in the sky. But what actually are they? Apart from things ejected from planets, there are other bits of debris knocking around in space too, aren't there?
Yes, in fact, only a very, very small fraction of them are thought to be from Mars, and the great majority are almost certainly pieces from the asteroid belt. That lies beyond Mars, a good bit beyond Mars, but not as far as Jupiter. And astronomers have known for a long time that there are a huge number of small planet-like objects in orbit around the Sun, going in circular orbits like the other planets in that zone.
Is this kind of debris left over from when planets were forming in the early days?
Yes. At one time, it was speculated that there was a planet there and it exploded, one single planet, and exploded into lots of bits. But the evidence we have now, it suggests a very different mechanism. The idea is that when the solar system first formed, there were no planets, but there was a newly formed sun, and surrounding it was a disk of dust and gas. And gravitational instabilities in that disk led to small planets forming, just a few kilometres across, tens of kilometres, gradually getting bigger, wrapping up like snowballs, getting bigger and bigger. And over a period of perhaps 10 million years, these small bodies aggregated and ended up as the planets that we know them. But for some reason...
So studying them does actually tell us quite a lot about how everything formed in the early days.
Absolutely.
4.5 billion years ago.
Yeah, so the asteroid belt is part of this early disk that never made it to make a big planet. So we're looking at things that formed in the first 10 million years of the solar system's history.
Now, you've brought some bits and pieces in for us to look at. So why don't you, Phil, talk us through, and then we can ask Ian what's actually...
Well, we've got some quite interesting samples here. I mean, we've got different types by the looks of it. I mean, one's quite dark and grainy. I mean, so that's one type, I presume.
Yes.
There's another one that's quite light and grainy. And there's another one here that doesn't look like rock at all. It actually looks like a sheet of polished aluminium or something like that.
It's steel. It's not far off stainless steel.
So it actually arrived in the form of unrefined steel.
Absolutely, yes.
So tell us about these samples. I mean, what actually are they and where did they come from?
Okay, well, I mentioned this disk of dust that was going around the early sun. Well, the dark one there, the grainy one, that's primitive material that's literally that dust, but it's aggregated into a small planet, and nothing much has happened to it since those first couple of million years, literally, of the solar system.
So all these little grains that we've got inside this bit of rock are actually the original grainy bits of dust and rock that formed into the original meteorite.
Yes, it turns out that the story is never quite as simple as one would like it. Those little grains themselves have a history, and a lot of things were going on in that first 2 million years, and they're not the very original bits of dust. They're actually being processed by heating and melting and other processes before they were made into that aggregate of grainy rock.
It's The Naked Scientist, Dr. Chris and Dr. Phil. We're here with you until 7. We're talking space science this evening. And if you'd like to ask us a question, we have in the studio Maggie Adairian and Ian Sanders. We're going to be talking about this at more length. If you would like to talk to them, 08459 25 2000, or you can send us an email, chris@nakedscientist.com. Let's just talk to Maggie. Now, satellites.
Yes.
The moon is our biggest natural satellite, but obviously we're talking about your field, which is artificial ones.
That's the answer.
What is actually involved in making a satellite and then getting it up there?
Well, I recently got into space science, and the main thing I noticed is lots of paperwork. Because one of the difficulties with launching something into space is that you want it to succeed. You can't just go out and tinker with it, or if you do, it costs an awful lot of money, like with the Hubble Space Telescope. So what you're trying to do is get something that is bound not to fail. So you build in lots of redundancy. And also, rather than going for cutting-edge technology, you try and use existing technology, which is well-known and well-established. So it's got lots of heritage. So usually a consortium of people will get together. So, for instance, I'm working on a satellite now for the James Webb Space Telescope, which is organised by NASA, but this is a subsystem which has been put together by ESA, and we're subcontracted to ESA, the European Space Agency, and we're building a detection system. So one of the exciting things about these projects is they work on a global scale, so they're scientists all over the world working on the James Webb Space Telescope. And what we'll do is we'll build an instrument, so we're building a detector system, and then we have to put it through very rigorous tests.
What's it going to detect?
This the one on the James Webb is actually looking at infrared, so it's actually a space telescope looking out into space.
Yep.
Another system I'm working on is for the European Space Agency as well, but it's an Earth-looking satellite, and this is actually designed to look at wind speeds through the atmosphere.
How on earth do you see the wind? Because it's invisible.
Yes, and that's one of the beauties of the system. It uses Doppler, so just like the ambulance going past, the tone changes as the ambulance goes past us.
Yeah.
What we're actually doing is looking at a laser beam. We shine a laser beam through the Earth's atmosphere, and it works very similar to to a radar. So it's actually called LiDAR, because it's like a light radar.
Yeah.
So we pulse a UV, ultraviolet beam, into the atmosphere, and it bounces off particles in the atmosphere. Mm-hmm. As it bounces off the particles, that light scatters, and we pick up the return beam, which is far, far fainter than what we send out. By looking actually at the Doppler shift, you can actually see a change in wavelength and work out how that particle is travelling in the Earth's atmosphere. And by looking at the time of the return, you can actually see, is it quite close to the Earth's surface? Is it high up in the atmosphere? So, for instance, if people fly kites, if you have the kite low down, it will travel at one speed. If you lengthen the string and it goes higher, the wind speed changes quite radically. So we're having a 3D view of winds through the atmosphere.
I was just going to say, does it look at just one altitude? Presumably not. No. You can actually look at a whole raft of different heights.
Throughout, yes, that's it. So just like with radar, where you look at different signals coming from different points in time, therefore you can look at right from the ground, so you get a ground return, which is the strongest signal you'll get, and then look at particles throughout the atmosphere.
How is this actually useful, though? Do we know that this translates into better weather forecasts, for example?
Yes, it does two things, because it does sort of local short-term weather forecasting, and so hopefully we can send this information to Michael Fish and he can give us a better weather forecast for the future. But it also is looking at long-term climate prediction. So, for instance, we talk about global warming. One of the things is there are many models associated with global warming, but you need data to verify them. And this Aeolus mission is set up to give a global coverage of wind speeds through the atmosphere and thereby able to verify these climate change models. So it's short-term and long-term data that we're getting.
OK, so you're designing this probe, It then goes aboard a satellite.
Yes.
It gets carried into space. When it gets up there, how does it actually get powered, for example? How do these things actually work?
Yes. So it depends on what sort of orbit you're going into, but they usually sort of launch into space. The systems I'm working on are going to be launched by a Russian launcher, and that's something I'd really love to go and see. The idea of all this sort of, this mass being launched into space. So it gets there, it's then deployed, and there's telemetry which sends signals to the satellite, asking it, for instance, to deploy its solar panels.
Yep.
You can get some satellites which are powered by nuclear energy, but the sort of satellite we're setting up is actually solar. So we'll have solar panels which will be deployed and then power up the systems on the satellite.
And they never end up in the dark, these satellites. Do they always have a supply of sunlight to keep them going then, or do they have batteries to back them up?
I think that generally they have batteries to back them up, because especially when you first launch, there's that initial period before the solar panels are deployed. So you'll have that. But depending on what sort of orbit you put it in, and also you can tilt your solar panels so that they're always picking light up from the sun.
OK. You're listening to Dr Chris and Dr Phil. We're here live on BBC Local Radio right around the eastern counties. And if you'd like to talk to us and ask us a question, we're talking space science, satellites and meteorites. 08459 25 2000 is our phone number. Shortly, we'll be discussing how we avoid the next Armageddon. In other words, if there's something on an earthbound course that's capable of wiping us out in the same way that something pretty huge wiped the dinosaurs out 60 million years ago, can we actually avoid it? Well, Stan Love is a NASA astronaut in Houston in Texas. He reckons he knows the answer, and we'll be talking to him very, very shortly.
Laying the facts bare, The Naked Scientists.
If you want to have a go at our kitchen science experiments, of course, you'll need a lemonade bottle, a torch and some water. You need to punch a hole in the bottom of the lemonade bottle and shine the torch through on the other side and let the water run out and see what happens. First person through on the phone with the correct observations, 08459 25 2000, will win themselves a prize. We have for you tonight tickets to the IMAX in London, and also we have to give away some Wiggly Wigglers vouchers to get your garden growing like there's no tomorrow. We are, of course, live on BBC Local Radio right around the eastern counties, taking your questions if you have them for us. 08459 25 2000 to talk to Maggie Adarin here in the studio, or Ian Sanders. They're experts on satellites and meteorites, respectively. And on the phone now from Houston in Texas, we have Stan Love, who's from NASA. Hello, Stan.
Hello.
Good evening.
Thanks.
Now, you reckon you have come up with a way to solve the problem of what would happen if we discover something a bit similar to what possibly wiped out the dinosaurs 60 to 65 million years ago. But what is it?
Well, my co-author Ed Liu and I have come up with an idea that would make deflecting an asteroid that's coming at the Earth a lot easier than some of the schemes that have been proposed over the last few years.
What sorts of schemes have been put forward, though? There's things like blowing them up, but that doesn't seem to work too well, does it?
Blowing them up has been proposed, but that's hard to do. Asteroids are a lot tougher in impact than you might think. They're like big flying bags of rubble, and bags of rubble do a great job of absorbing impact and explosion damage. It's hard to calculate exactly how much explosion energy you'd need to break up the asteroid, and if you got that calculation wrong and all you did was bounce the rubble a little bit and then it all fell back together under its own gravitational attraction and was still coming at us, it'd be kind of a problem.
So what's your solution?
Our solution is to use a spacecraft to gradually tug the asteroid out of the way. Now, ideas like this have been proposed before, where you sort of nuzzle up to the asteroid. It's got such weak surface gravity that it's hard to just plant a spacecraft on the surface the way we land on Mars or the Moon. And it's possible to nudge an asteroid out of the way like that. But once you've landed, not only do you have to worry about attaching, but the asteroid's rotating. So the thrust that you've gone to all the trouble to get out there and landed is now hosing around in circles like a lawn sprinkler. Our alternative is that you, instead of touching the asteroid, you sidle up next to it and then turn on a very low-thrust engine that just manages to balance the weight of the spacecraft as it's being pulled on by the asteroid's gravity. And you just hover there. And as you hover there for months or maybe a year, the very slight gravitational pull between the spacecraft and the asteroid will change the asteroid's orbit enough that if you got there ahead of time, say 20 years in advance, that after that orbit change had built up over 20 years, you would miss the Earth instead of hitting it.
Do we know of anything that's likely to actually be amenable to this kind of therapy, let's say, at this stage? Are there any things on Earthbound courses within your time frame for actually deploying this kind of measure?
Right now, there's nothing that we know of that's going to hit us. But there is an asteroid that we are going to be paying attention to over the next couple of decades. It's 99942 Apophis. It's going to come swinging by us in 2029, close to the Earth. And if it passes at just the right distance from the Earth during that swing by, it will get kinked onto a new orbit by that close approach with the Earth that would bring it back to hit us in maybe 7 or 8 more years. Now, we don't know yet whether or not that's going to happen. The probability of it happening is very small, something like 1 in 5 or 10,000. But we'll be keeping an eye on that asteroid. If it should turn out that it's headed on that collision course, then if we could get a spacecraft like the one we're describing, what we call a gravitational tractor, get that out there before the close approach, a tiny change to its path just before that approach will translate into a very big change in its orbit after that close approach. So you can sort of multiply the effect of your deflection scheme by doing that.
Is technology actually up to being able to do this at the moment, or is this very much a speculative thing that could work if we have another set of technologies coming online in the next X number of years?
Stuff of the kind that we're proposing, at least in our Nature paper, hasn't been flown yet. The baseline gravitational tractor we were talking about is about a 20-ton spacecraft, which is very big, powered by a nuclear reactor, which has been done a few times but is not commonly done today. So these are not mature technologies, but NASA was proposing to put together just such a spacecraft to fly out to Jupiter and go into orbit successively around Jupiter's big moons. It was the Jupiter Icy Moons Orbiter. So the technology is not mature, but it's within reach.
We're going to have to leave it there, Stan, but thank you very much for joining us this evening and telling us about this exciting idea. Yeah. I just hope that we don't need it in the near future, if you see what I mean.
You're very welcome, and I know just how you feel.
Thanks for joining us this evening.
Sure, bye-bye.
NASA astronaut Stan Love telling us about their gravitational asteroid tractor, which we hope will be able to pull big things on Earthbound courses out of our way in the future. You're listening to The Naked Scientist, Dr. Chris and Dr. Phil. We're here with you until 7, joined in the studio by Maggie Adarin and Ian Sanders. We're talking satellites and meteorites, and if you'd like to get a question to them, we'll start taking your questions now. 08459 25 2000 is the phone number.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
Good evening, Les.
Good evening.
You're live on The Naked Scientist. What's your question?
Asteroids, do they have sort of like a maximum speed, or can they keep accelerating as they gravitational shoot off anything that happens to get in their way?
I guess that's one for you, Ian.
Yeah. Well, there's a number of aspects. The asteroids are tumbling in space. They're spinning around, and an interesting thing is that they're all spinning rather slowly. That is consistent with them being loose piles of rubble. They're not solid objects. When they come to Earth, meteorites coming to Earth tend to travel rather fast, around 20 kilometres per second. There's a maximum of 70 and minimum of about 10. And the net result of that is that they make this wonderful fireball effect. If a big one comes, the atmosphere doesn't slow it down, and that's when trouble happens, because that'll come all the way down to the surface and explode. That's what we don't want.
Have you any feel, actually, Ian, for what sorts of size objects you need in order to do devastating things on Earth?
Well, to give you an idea, the youngest, one of the best studied meteor craters is the one in Arizona. That's just over 1 kilometre wide, and the object there was about 30 metres wide.
Good grief! So that's a considerable difference, isn't it? 30 metres produces a kilometre crater.
That sort of size, yeah.
So what sort of size would you need to wipe out the dinosaurs, for example?
The estimate is about 10 kilometres for the meteorite, the asteroid, I should say, that struck 65 million years ago. Yeah.
Les, do you want to have a go at the quiz?
Yeah, I'll have a go, please.
OK, here we go. The most frequently broken bone in the body is the wrist. Do you think that's science fact or science fiction?
I think it's a bone within the wrist, yeah. I'll go for wrist fact.
So, yes, I'm lucky. Actually, the most frequently broken bone in the body is the collarbone. Usually from people falling over and putting their arms out, and then the shot goes all the way up, breaks the collarbone.
You got another go, Les? Ready?
Yeah, I'll have another.
Malaria is the commonest disease in the world. Fact or fiction?
I would certainly got to get on that way. No, cold is the commonest, so I'll go for a cold, something like that, so it's fiction.
You're correct, it is fiction, but it's not the cold. Actually, the most common disease in the world is tooth decay. It gets pretty much everybody at some point.
Including me.
Les, 1 out of 2. Well done.
Okay.
Thanks for your question. If you want to ask us a question here on The Naked Scientist, 08459 25 2000, or email me, chris@nakedscientist.com. Let's have a quick chat to Simon, who's in Wellingborough. Good evening, Simon.
Hello, mate. How you doing?
Very well, thank you. Thanks for joining us on The Naked Scientist. What would you like to know?
Yeah, well, I've been reading a daft, light fiction novel.
Yeah.
And then, by coincidence, I was talking to my brother-in-law last night, and now your programme's come on. And I just wondered how dependent we are on satellites. I.e., if somebody put one of those computer bugs in them, and they came down, and what would happen?
Maggie?
Yes. It could vary. I think communications is big business in terms of satellites, so that could have a very large impact. I mean, losing some of the television channels I wouldn't be so upset about, but I think communication would be the big impact.
I agree with that.
Yes. In terms of other impacts, I think they're usually workarounds, and that's what we spend, as a scientist, that's what I spend my life sort of doing, trying to find workarounds. So I don't think it would be the end of civilization, but I think, for instance, money changes and things like that would be brought to its knees for a while, but would find ways around, and so we would definitely recover.
And it's probably also something you sort of went on very slightly earlier. We don't know what the military are up to.
Yes.
Yeah, because there is I don't know if it's an urban myth, but everybody's scared about their certain Far Eastern continent at the moment.
Oh, yes.
Yeah.
So, monitoring and things like that are all done via satellites. So, but I think satellites are generally run on very different computer systems. So, although you might take a small proportion of satellites out there, you wouldn't take the majority out. So, I think we're quite safe.
Oh, right. Thank you.
Simon, do you want a quick go at the quiz?
Yeah, fine.
OK, here we go. The jugular is an artery in your neck. Is that science fact or science fiction?
That's fact.
Sorry, unlucky. The jugular is in fact a vein and not an artery. The artery in the neck is actually the carotid.
Yeah, the carotid. You unfortunately fell for that one, Simon, but you got another go. Are you ready?
Yeah, too obvious.
The blue whale has the longest gestation period, in other words, the time it takes to have a baby, out of all mammals. Is that science fact or science fiction?
Fiction.
Absolutely correct. In fact, it's the African elephant that lasts the longest.
Yeah, honestly.
Carried its babies for a good 2 years, so that's a long while, I think.
Well done, Simon. 1 out of 2. You're equal first at the moment.
Lovely job.
Thanks for appearing on the programme.
It's a fabulous programme.
Thank you. We've got just time to sneak in Treasure, who is in Essex. Good evening, Treasure.
Hello there.
What's your question?
I look out of my window and I'm facing slightly southeast. If the moon is up, it's to the right of the moon. There is something that appears to be a satellite. I've been watching it since October. Starts very low in the sky. It's one of the first things to appear before the stars. It gradually moves round to the west, rising in the sky, and it disappears early hours of the morning. It appears to flash red and sort of white, and it looks as if something's turning to make these lights flash. Is it a satellite, or what have we got out there?
Maggie, what do you think?
Yeah, I think it's more likely to be a planet. When planets are low in the atmosphere, because they're travelling through such a large depth of atmosphere, they twinkle. That's why we see stars twinkle. And I've seen them, and sometimes they twinkle very bright colours. So I think you're more likely to be seeing a planet than a satellite.
Yes. Will it stay there with us, or will we lose it? Or?
You will eventually lose it, because they're all orbiting around the sun. Depends on our position and the planet's position. But eventually it will move on off and probably won't be visible for a while.
Treasure, quick go at the quiz?
Yes, please, yeah.
The commonest bird in the UK is a blue tit. Is that science fact or science fiction?
That is fiction. Oh, dear.
Unlucky. It is, in fact. That's the one that you're most likely to see in your back garden.
Yep.
Next question, Treasure. Silkworms eat blueberry bushes. Is that fact or fiction?
That is fact.
Sorry again, it's actually mulberry bushes that they eat.
They were nasty, weren't they?
They were nasty.
But look, it's been great having you on the programme, OK?
Thanks a lot.
Thanks for joining us.
Stripping down science.
OK, let's do it.
The Naked Scientists.
is Dr. Chris and Dr. Phil, and if you'd like to ask us any questions about anything to do with space science, we have just a couple of minutes to go before we head back to the school in Billericay to see who has got the right answer for kitchen science. On the line now is someone who thinks they have. That's Mary, who's in Kettering. Mary Rose, good evening.
Good evening, Dr. Chris.
Great to have you on the programme. You've had a go at our experiment, have you?
Now, I must say, at Billericay, they were extremely organised, unlike me with my knife, trying to do a hole, myself and Simon, with a hole in the bottle.
Oh.
It's a bit of a Heath Robinson affair.
Oh, dear.
But we had a try.
So you didn't use a wine bottle then, Mary Rose?
I'm drinking from the wine bottle, but I got a plastic bottle.
Oh, right. Is your name really Mary Rose?
It is, and my mother knew nothing about the ship.
I was going to say, because that would be a bit of a bad omen, wouldn't it?
Wouldn't it just? No, my mother thought, first of all, of the Mother of God, because I was a tiny wee tot. She wouldn't think it now.
Right.
But no, she didn't think of Henry VIII and his famous ship.
Oh, but at least the Mary Rose came back up again, and it's now in a museum. It looks very nice. What's left of it?
Yes, it's down in Plymouth, I think.
Well, look, tell us what you found when you did the experiment.
Well, when we did the experiment with Simon and the light, the light followed the water out. That's what happened with me. Well, that's what it looked like was happening.
OK, so you got the bottle of water.
We got the bottle of water.
You made a hole near the bottom, put your finger over it.
Absolutely.
Shone a torch or something in the other side.
Yes, I shone a torch through the other side. And
yep.
It looked as though the light came out with the water and
right.
came out of the hole.
And where was the actual light? When you say the light came out, where was the actual spot of light appearing when you looked?
Well, it was appearing, it looked to be in the water. Actually, with the water coming out.
Inside the column of water coming out?
Yes.
Right.
Well, that's what happened with mine.
OK. It sounds pretty good. Shall we... I'll tell you what, then. Why don't you hang on the line? We'll go back to Billericay and talk to Derek and Dave and the guys there, see what they find and get the explanation, and then we'll see if you've got it right. What do you actually think's going on? Why do you think you're seeing what you're seeing?
I don't. I'm no scientist. I'm a geographer, and I know nothing about science. I don't know what is actually happening.
Well, let's find out, and let's find out from Derek and Dave what the explanation is, and then we'll come back to you. Hang on the line, OK? Derek, what's the answer? Are you still there?
Hello again, yeah, welcome back to Billericay School, and we are poised here and ready to find out what happens when we let the water drain out of this bottle and shine the torchlight through the hole that we made as well. So, nothing more to be said. Dave, shall we do it?
Let's go.
OK, so Simon, Andrew and Rachel are ready with it, so please tell us, guys, what you see when you let go and let the water come out with the light kind of coming through behind it.
OK. You can see the light on my hand, which is catching the water from the bottle. And this is because...
Go on, Andrew. Come on, Andrew.
Well, the light is clearly travelling through the water.
So even though the water's gone round a corner, the light's still staying inside the water.
Yes.
Yeah, I mean, what we've got then is we've got a thin stream of water which is coming out of the hole that we made. So the stream is, only a couple of millimetres across or something. But even though it bends downwards, being pulled down by gravity, we still see the light is coming out at the end of that stream of water. So Rachel has actually got her hand under the end of the stream, and there's a little circle of light where the water meets her hand. So there we go. The light seems to have bent round through the stream of water that we've got. So what is going on here, Dave?
OK, let's move over to my tank of water over here.
OK, so Dave's actually set up a tank of water to help us explain what's going on here. And it's a circular tank. It's probably about 14 inches across, and it's full of water. And it's kind of placed on a space between two tables so that we can actually get a view from underneath it. And it's actually made out of glass as well. So we're about to be doing some viewing from underneath it, I guess. So, Dave, then, what do we do?
OK, Andrew, could you climb underneath the table and look up through the surface of the water and see what you can see?
You can see right through the water.
So basically you can just see straight through to the ceiling. It's behaving as you'd expect. OK, now, Simon, could you just look through the water, just look it up at it at a very small angle? So
from down there?
From through the side.
OK, so Simon is almost side on, really. He's not looking from directly underneath. So if you look at the underside of the surface of the water, what can you see there?
Just like his hand, but it's below the water.
So looking up under the water at a small angle, it behaves like a mirror.
Yeah.
This is called total internal reflection. If light comes out of something like water at a very small angle, instead of going through it, it will actually bounce off. In fact, an incredibly high percentage of the light will bounce off, and it's almost a perfect mirror.
OK, so that means that if we look, let's say, straight down at a tank of water or something, then we'll see straight through it. But if we look at a very shallow angle, we're almost looking across it, then this means that actually the water's like a mirror at that point.
It actually works best if you're looking from the water out, but yes.
OK, so the best thing to do is do what we've done and try and have a look from underneath a transparent tank, like a fish tank. See if you can get it between two tables like we've done. And if you just look up underneath it at a very shallow angle, you should actually see that the surface of the water from underneath acts like a mirror.
Or if you're in a swimming pool and you're looking out the top, sometimes you can see the surface acting like a mirror.
So then, this thing we did with the tube of water and, of course, fibre optics, how does that all relate to this then?
Well, when you shine the light into the tube of water, it's going to meet the water at a very small angle, so it's going to reflect. So it'll keep reflecting again and again inside that tube of water till it comes out to your hand. This is exactly how a fibre optic cable, which transfers most of your phone calls and the internet, works. All you do is you shine a light in one end, it bounces inside this long, thin glass tube, and it comes out the other end, even though the glass tube's gone around lots of corners.
OK, so we had a tube of water which was very slightly curved because it was coming out of the lemonade bottle, horizontally at the start, and then gradually it curved down and made its way into the sink. So that wasn't curved enough for light to leave it. But I suppose if you have a fibre optic that curves enough, can light actually leave it, and it doesn't manage to carry the light?
Yeah, that's exactly right. In fact, apparently it's a way of people hacking into fibre optic cables. If they bend the fibre optic cable just enough to let some of the light out, you can put a sensor in and work out what information is travelling through the cable.
But, of course, we're not recommending anyone does anything like that. But, who would, frankly? So, Simon, then, you were the man looking from underneath the water. So is that clear now? Has Dave's explanation cleared that up?
Yes, it has, yeah.
Hey, good stuff. OK, then. So, Andrew and Rachel, did you enjoy our experiment?
Yep.
Yes.
So you can do it at home.
Yeah, very interesting.
OK, and are you going to be going home and doing it yourselves?
Perhaps.
Of course.
Oh, OK, very good. Some very keen participants there. That's great. Well, thank you very much to the Billericay School. And they are so keen, we are actually going to round this whole thing off with another fantastic cheer from this school. So it's bye from Dave, bye from me, and bye from the Billericay School.
Thanks very much, Derek, and everyone at Billericay School for that. Let's find out if Mary Rose is pleased with her result. Mary Rose?
Well, yes.
Well done.
Isn't that fantastic?
You've won, and we'll give you some Wiggly Wigglers vouchers. How about that, to make your garden grow beautifully?
That will be wonderful. Just what I need.
Thanks for taking part in The Naked Scientist.
Pleasure.
Right, just time to sneak in one very, very quick question from Rose. Hello, Rose.
Hi.
What's your question? You've got 10 seconds.
Why did you send a dog into space?
Right, go on, Maggie. You've got 10, 15 seconds to answer this.
The reasons why we send dogs into space is because they're so intelligent. You can train a dog to do all sorts of things, and so that's why we want them to go out there, because they can give us feedback while they're up there. It's a bit unfortunate, but they're very bright.
Well done to everyone who's taken part in tonight's programme. Our winners this evening, we have Mary Rose from Kettering on Kitchen Science, Simon in Wellingborough for our Fact or Fiction. Well done. Thank you, everyone, for taking part. We need your science questions for our science Q&A next week. Please, in the meantime, have a great weekend.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.